Okay, so we can get started here. This week, our objective is going to be to complete the discussion in worksheet 7. There's a fair number of exercises scattered throughout that worksheet that deal with various aspects of differentiation. And then we're going to apply that in worksheet 8 to local max-min problems. So you have worksheet 8 up on the Moodle site. And our quiz, our 5th quiz, will in part complete worksheet 7, and I don't know how far we'll get into worksheet 8, but I'll know by Thursday, so I always limit it so that it's what we're actually doing. Okay, so today I want to begin the discussion of the chain rule. We will need this moving forward. In one variable calculus, we study the chain rule. And if we say it geometrically, it's a classical problem about differentiation of composites of functions. So in a flowchart idea, I've got functions that I perform in sequence. The first one followed by the second one. Okay, what we call a composition, or as I like to humorously refer to it as the FOG, F composed with G. And the chain rule in its one variable context is a statement about how I calculate the derivative of the composite. Okay, so our chain rule from one variable calculus is that this differentiation of the composition is the product of the derivatives in this sense. Geometrically, we say slopes multiply. Okay? But that's something that we live and die by in calculus 1 and 2. We have to use it all the time. Well, what happens in multivariable context? Well, I say in a nutshell, the same thing. But the big difference is, what does multiplication mean in the multivariable context? And in a phrase, multiplication means dot product. So we're going to use the dot product to develop the chain rule in a vector sense. And once you see it and organize it that way, it's very straightforward to understand. Okay, so that development is what we're going to do today. We're going to see what is the multivariable version of the chain rule. And in essence, it's this, but the meanings of these terms change. Okay, and multiplication has to be reinterpreted as a dot product. So our interest is in this type of situation. And let me try to see if I can give you a concise description of this. We have a pair of functions now, g, okay, where g goes from some Euclidean space to some other Euclidean space. Okay, we can easily imagine different situations like this. And then it's followed by f, a second, which takes me from the codomain of G to some other possible Euclidean space. Okay. Now, in last week, we talked about the idea of a derivative matrix, and that a derivative matrix is made up of so many rows and so many columns. The rows, in this case, are going to be gradients. Okay, the columns are these total partial derivatives. Okay, so we would have this idea of calculating the derivative matrix of the composition at a point. Okay, so my point would be in the domain of my first function. And that this is going to be a product of matrices. This is going to be a matrix product. Be a matrix product. And now, if you've had a little bit of linear algebra, you've multiplied matrices. But my bet is you would never taught about matrix multiplication in terms of dot product. And it becomes a chicken and egg question. Why do I multiply matrices the way I do? Okay, and the answer is because of the dot product. Oftentimes in linear algebra texts, they kind of ignore that. And it seems mysterious. Okay, so this matrix product is going to be a collection of dot products. By parallel, it's behaving in the same way that it did in one variable, except this is a 1-by-1 matrix. Okay, they're easy to multiply. That's just multiplication of numbers. This is a more complex product, but when you think of it as dot products, it becomes easy to understand. Okay, so I want to spend some time here explaining that, and then looking at it in some special cases that we'll use for other types of measurements. Okay. I want to share my screen for a moment here. In worksheet 7, on page 7, it's titled the chain rule. The first example that I give here is to give you a feeling for how these dot products will actually work. Okay, so when I talk about multiplying matrices, I cannot always do it unless there's a certain compatibility, that the matrix on the left has to have the same number of columns as the number of columns of the matrix on the left has to match up with the number of rows of the matrix on the right. And in this particular case, if I had a 2-by-3 matrix and a 3-by-2 matrix, that's going to be a case that will show up for us. My left matrix is made up of 2 rows, but each row has 3 numbers in it. So if you start to think of these rows as gradients of scalar functions, that's what these will be in practice. The matrix on the right will have 2 columns, but each column will have 3 numbers in it. And so what I say here is when you form the matrix product of row I by column j, what you're literally doing is taking the dot product of row I with column j. So since dot product has a geometric meaning, that's going to be telling us something about rate of change. So that's the first takeaway here, is that you're going to be dotting the rows on the left with the columns on the right. Okay. And then how many such dot products do you have? Well, in this case, there are going to be 4 such dot products corresponding to the number of rows on the left with the number of columns on the right. And so they give me the entries in the actual matrix. Okay. Now we're going to bring this home with calculus, where these matrices are going to be derivative matrices. Okay, matrices that are made up of gradient calculations. Okay. Now let's scroll down just a little bit. We're going to be interested in 4 different cases of the chain rule throughout this course. And the first case is where I go from R to Rn, and then from Rn back to R. So what type of case is this? Well, the G process is some kind of curve, what we call a particle moving around the space. And the second function is some kind of scalar function of that many variables. So R to R2 to R, or R to R3 to R. So what does the chain rule look like when I write out the derivative matrices there? A second case will be Rn to Rn to R. Okay, that'll come up when we're studying vector fields later on in the course. Another example is Rn to R to R. And then the last of the basic ones is Rn to Rn to Rn. So I've got, in this case, my derivative matrix will have the same number of rows as columns. That would be the square case. Okay, so in the first example here, I give you my first function g is going from R2 to R2, and the second one is going from R2 to R3. And then I just ask you to use the chain rule to calculate the partial derivative matrix at a particular point. Okay, so part of your learning here is you're going to have to work your way through. What do I mean by this? So there's a learning curve there. So in this first exercise, I kind of walk you through the calculation one step at a time. Okay, and you could try to do it on your own. Okay, so here, I'll hide my screen here, and we can work it longhand.
Is there a typo in that one? In column 2, row 3, the final element there? Shouldn't it be like 4y cubed?
Well, let me work through that. And I have a disclaimer on typos. They're all my fault. But that's why I go over these things in class to find out in the most embarrassing way that I have a typo. So let's go through it, Justin. The first part of this is that G is taking a pair of numbers and creating another pair of numbers. So I like to think of this as a flow chart of information. I'm going to have, that's how the calculation is working at stage 1. Stage 2, that's F, it's going from R2 to R3, and its description is I start with a UV, and I create 3 numbers in order, U plus V, then U, and then V squared. So this process, visually, you see how the process is going to work when I do it in sequence. When I do it in sequence, U becomes x squared plus 1, and V becomes y squared. So if I were to write this out as a composition, okay, what do I get? Well, I'm going to add U to V, which means I'm going to add these 2 numbers together. So this becomes x squared plus y squared plus 1. That's the first number. Then the second one is I put U here, where U is this number. And then the third one is I square whatever V is. So I'm squaring y squared. What should I get? Well, y to the 4th. Now, let me take a look. I actually didn't write that out, but that's what that is. That's what that would be if I wrote it in terms of the original variable. Okay, now without the chain rule, I can just go through the calculation of the derivative matrix just by brute force here. So let's go ahead and do that and calculate the derivative matrix of the composition at an arbitrary xy. Okay. Okay, so how do I do that? Well, if you go back and take a look at the process here, I have 3 component functions. I've got a first one, a second one, and a third one. I'm going to take the gradient of each component, right? Because each component is a scalar function of two variables. So I can calculate the x and y partials of each component. And they form my matrix. Okay, so let's do that. So see if I can get some volunteers. So the gradient of the first component, it forms row 1.
You get 2x, 2y.
That's correct. Good. 2x, 2y. The gradient of the second component is what? Well, it would be 2x. But then the y partial, Calvin, is what?
0.
0, right. Calvin's my go-to guy here when I want to call on someone. Instantly, right? Okay, just teasing. What's the gradient of the third component?
0 for y cubed.
0 and 4y cubed. Okay. Justin, there is a typo.
Yeah, I was doing the matrix. This is kind of neat doing it this way. I did the matrix multiplication and I was like, wait, I got 4yv, but then when you plug in the y for the v, you get the y cubed. So
You know, I should just, I'll go in afterwards and make the correction. But yeah, so that's correct. Okay, now I can calculate this brute force. So that's, I mean, I can write out the composition and then I can do the derivative matrix as if I never needed the chain rule. But the chain rule relates certain information conceptually. It said that total derivative it arises as the product of the total derivatives of the intermediate steps. So that gives you a second way to do the same calculation. So you've got to arrive at the same answer. Yes.
Could you go once how did you get the composition of F of Z?
Okay, so once again, how did I get the composition? Okay, well, if you watch the flow here, x and y are being mapped to x squared plus 1 paired with y squared. The second step is described as, well, since I'm already using x and y, I'm going to use, as my variables, I'm going to use u and v. So, well, this function takes u and v, and it creates 3 numbers in this order. So when I do this composite, it's specifying that I want u to be x squared plus 1 and v to be y squared. So once I write this out, where u and v mean this, I get this right here. Okay? Okay, so the chain rule tells me that this derivative matrix is the same as this product of matrices, where product of matrices is going to involve a collection of dot products. So we can calculate these independently and then do the dot products, and we're supposed to end up with this. Okay? So in the actual worksheet, I had you going that way. All right, so let's go ahead and do that.
Is this supposed to still be on the surface?
Well, there's no surface here. There will be surfaces later on. Right now, we're just taking derivatives at arbitrary points in space.
So it's not a normal?
So that we're not, at the present time, that's not a consideration. We're not looking at surfaces. We're just calculating these rates of change at arbitrary points in the plane.
Okay.
But hold your horses, that's going to come in later on. And I'll point that out. Okay, so we have to write out what these two derivative matrices up. So let's do the G one first. Okay. So if I do the G one first, what are the partial derivatives of the two components?
Your first row is going to be 2x 0, and then your second row will be 0 2y.
The other one's going to be 0 and 2y. Okay. Now let's do the derivative of the F map, okay, relative to the original variables u and v, because you might find that easier initially. So if I said, find the derivative matrix of these three components, in other words, three gradients, what would the gradient of the first component be? So if I said take the gradient of u plus v, so I'm taking the partials relative to u and v, what would they be?
1 and 1.
1 and 1. How about the gradient of the second component?
1 and 0.
1 and 0. How about the gradient of the third component? 0 and 2v. Okay, so notice that on the left, your matrix has 3 rows. Each row consists of 2 numbers. On the right, you've got 2 columns. Each column consists of 2 numbers. So we're going to take the dot product of row 1 with column 1, row 1 with column 2, and then move down. Row 2 with column 1, row 2 with column 2, and then row 3 with column 1, row 3 with column 2. And so we'll end up with 3 rows, 2 columns, just like we had up here. So let's do that. Okay, so we'll do that matrix product. And what do I get? What is the dot product of row 1 with column 1? Any volunteers? Dot product of row 1 with column 1. What do I get? 2x. Uh-oh, right there. Okay, now let's do row 1 with column 2.
2y.
And y. And notice. Bingo. Okay, now let's move down. Row 1 with column 1. Row 2 with column 1, excuse me. And I get 2x. And then row 2 with column 2. And what do I get?
0.
So what that's telling me is that my gradient of the second component of the f function is perpendicular to the partial derivative of the first guy with respect to y, because the dot product is 0. So that idea of the geometric meaning of dot product will start to come in, but just mechanically, make sure I have mechanics down, that's all I've done. Okay, now repeat this one more time. I've got row 3 with column 1, and what do I get? I get a 0. And now, finally, row 3 with column 2 on the right, what do I get? I get twice y times v.
3 before.
Hold on. Oh, it should be 4, right, yeah. Yeah, because 2 times 2 in most countries is 4, right, good. Well, over here I had 4y cubed. And so the question becomes, is 4yv the same as 4y cubed? That's my question, right? What has to be true about v?
Has to be y squared.
V is y squared. Because this was done in sequence. So they are the same, aren't they? Okay? So what I always do this using the original variables, and then I specialize them according to the composition. And so, yeah, this is the case because v is y squared. If you go back to see the original sequence, I took v to be y squared when I did it in sequence. Okay, now at the end, I wanted to evaluate this matrix when x and y are both 1. Because I just wanted to do it at a particular point. Okay, so if I was doing it when x and y are both 1, well, I'm getting a 2 and a 2 here, a 2 here, and this becomes 4, right? Okay, so this is the mechanics of how the chain rule works. You'll find yourself using your chain rule from one variable calculus when you're carrying out these calculations. I've given you a whole bunch of exercises in here that are just to take you through your paces of doing them. So I would say, let's start practicing them. And then in the supplemental problems, I gave you a few more just so you can do it easily. Okay, in problem 2 here, I give you a scalar function of 2 variables. Okay. And I compose it with this function g. So I'm going to share my screen here for a second. So in the statement of the problem here, I say take a scalar function of 2 variables, okay, and compose it with this function g. And the first thing I ask you to do is to calculate the gradient of the composition. Okay, and I take a pre-calculus approach here in this problem. I constantly am asking you, what's the domain and range? Because if you're not reading that information correctly, this is hard, okay? But if you read this information, it organizes it in a way that you calm down and you see what you're supposed to be doing. So these in typical textbooks, they won't ask you questions like that. They expect you to never forget it. But in practice, we forget things like this. So let's answer them, because it'll get us to the right, to where we need to be. So I have this scalar function of 2 variables that I'm composing with this function g, and I say, what are the domain and range of f? I could ask the same question, what are the domain and range of g? So I'm going to stop the screen share here and go through that process. So the g process here, it took a pair of numbers, which I called r and theta. And what did it do? It says you take r and theta and you create this ordered pair, r times cosine theta, and then r times sine theta. And then f was just some scalar function of 2 variables. So f's domain is R2, and the codomain is R, because you're taking 2 numbers to produce 1 number. Okay, so this is f of xy. Sometimes people might write this as simply z, because z comes after x and y. So the thrust of the problem here is the two-step process. I called H, just because H comes after G. All right? So by meaning, it's that. Okay. Now, if you look at it in sequence, what is H doing? Well, it's starting with a pair of numbers, and you're ending up with a single number. Right? Notice that when you display the information this way, it tells you that from the reading, that I started off with a pair of numbers and I end up with one number. So that's telling me I've got a scalar function of two variables. So theoretically, the gradient is going to be what? The gradient of H will be the two partial derivatives, Hx and Hy. Or in this case, Hr and H theta, since they're the names of my original variables. So I'll use that. Hr and H theta. Okay, let's pick a particular f. Okay, so thus far I didn't give you a specific f. I gave you a specific g, but not a specific f. So let's pick one. Okay, suppose f is f of x, y is, say, x times y. So question is, what's h in that case? What is h of r theta going to be? So if I go through the process here, the first step is written down for me. I take my r and my theta, I create this x and y. Then the second step is to take those numbers and multiply them. So if I write that out, what is this? Well, it'll be r squared times sine theta times cosine theta. Right, because x is r times the cosine of theta, y is r times the sine of theta. This function that I made up here, I said, well, take the function that just multiplies the coordinates, just to have a sample function. Then that means I'm going to have an r squared, and then I'm going to have the sine of theta and the cosine of theta. Okay. If that's my f, what's the gradient in that case? So now we're back to first principles. When I calculate a partial derivative, all other variables, other than the indicated one, are regarded as constant. So if I'm differentiating this with respect to r, what do I get? I get 2r times sine theta cosine theta. Okay, that leaves me with the theta partial.
You're gonna use the product rule?
You bet. I'm gonna have, you knew I was gonna throw a product rule in there, right?
Right.
'Cause by the way, that's because of the nonlinearity. The nonlinearity is part of the physical world. So product rule, we need it. So product rule tells me that this is going to be r squared times cosine squared theta. Okay. And then it's going to be r squared times the negative of sine squared theta. And if I do a little bit of factoring, I can factor out the r squared. Okay, this is not important at this point, other than I'm just taking trying to get a sense of your understanding of some things. Do you recognize cosine squared subtract sine squared? That's a trig identity. What trig identity is it? Does anyone know?
Is it cos 2a?
What now? Speak up.
Cos 2a?
It's the cosine of twice theta. Okay. Now that's not significant now, but later on we're going to use this calculation again, and these angle formulas start to creep in. But if you got this far, perfect score. Okay, what does the chain rule say in this case? Because it's a composite, I can also calculate this using the chain rule. So let's now think about this calculation in an entirely different way. We have the first way, what I call the direct way, but then we can build it out of the two derivatives of the intermediate steps. And that carries merit. Okay, so let's do that. Let's calculate the derivative of the G matrix at R theta, and then on the left, I'm going to multiply it by the derivative of the F matrix. And the derivative of the F matrix is just the gradient. So I'm going to literally, it's going to be gradient of F multiplied on the right by the derivative of G. And what we'll notice is that the number of columns of the gradient will correspond to the number of rows of the G matrix derivative. Okay, let's do that. Let's calculate that out. What is the derivative of the G matrix in this case? Well, I've got two components here. The first row is the gradient of the first component. The second row is the gradient of the second component. So those are partial derivative calculations. So let's see if we can get that going. So who wants to help me here? I want the gradient of the first component of the G function. So I'm going to calculate an R partial and a theta partial.
It's cosine theta and then minus R sine theta.
Yeah, that's right. Cosine theta and then minus R times the sine of theta. Okay, now go to the second component. Well, my bet is you're going to just tell me sine theta and then R times the cosine of theta. Okay, now my F function was what? My F function was evaluate F at x, y, and you get multiply the x and the y together. So I want to calculate the gradient of the F function. So my function here that's my function, right? So if I want to take the x partial of that, what do I get?
Y.
I get y. Then take the y partial, I get x. Now notice, other than for the comma, okay, when I write it in this way, I agree to omit the comma, but I have one row with two entries, and then on the right, I have two columns, but each column has two entries. So now I do how many dot products here? Well, I'll be dotting this row on the left with both of the columns. And so that'll produce two numbers, which is the gradient of my H function. Okay, so let's go ahead and do that.
Just a quick question. Do we rearrange the gradient matrices so that they can be multiplied?
Well, I wrote the gradient, it is a single row, right? So the gradients on the right are the rows. The columns are the total partial derivatives. So one way to think of the right side here is this is the total partial relative to R. And this is the total partial of G relative to theta. That'll have geometric meaning later on when we go back to surfaces. But for the time being, it's just you're calculating the gradients of the two components, they form the rows. And the second function has only one component because it's scalar value, but it has two partials. And so traditionally, we write that horizontally here on the left. Okay, now I can do the dot product. If I do the dot product of this with column 1, what do I get? Well, I get y times the cosine of theta added to x times the sine of theta. Okay, now I just leave myself some space. That's why the comma was invented, just to visually make that distinction. I'll put the comma there just for that reason. Now I do the dot product of row 1 here on the left with column 2, and I get negative ry sine theta added to rx times cosine theta. And that's my second calculation. Okay, now if you compare that to what we got a moment ago, at least initially they look different. So I could ask myself, how could this first calculation here end up being 2r cosine sine theta cosine theta? What would have to be true for this fellow here to be the same as that one?
Log is equal to our sine theta.
Yeah, see, the secret's right here. What is x and what is y? X is r times the cosine of theta, and y is r times the sine of theta. And so this is x and that's y. Okay. I'm compact my g derivative, that first, my f derivative is at g of r theta. So where that means that the x value is r cosine theta and the y value is r times sine theta. So the moment I plug that in for x and y, I get exactly this right here. And likewise, if I take y here to be r sine theta, this becomes negative r squared sine squared theta, which is what I was picking up over here. And x is r times cosine theta. So this gives me r squared cosine squared theta. Okay, questions? Some people are being quiet.
I have a dumb algebra question.
Oh, there are no dumb algebra questions.
So, how do you know in your identity cosine 2 theta that negative sine squared isn't just equal to sine squared? Like you would know with negative 4 squared is actually positive.
Well, if I understand your question, you're really asking about the trig identity. And I'm happy to talk with you about that offline, how I know that. But that comes from the double angle formula. And I could take you through that derivation.
I mean, when you square any number, it becomes positive. So why isn't sine squared positive?
Well, sine squared of theta is positive.
Or subtracting the whole quantity.
So I'm not subtracting the whole quantity. It's the difference of the squares.
I think what I'd done in the quiz was I thought that it was just negative sine squared, not minus sine squared. You know what I mean?
I think I do, but I can talk with you about that offline. That'd be great.
Okay.
Let's definitely do that. Okay. So here's 2 examples of the chain rule, and in the remaining time here, I want to tie this back into what you were doing in worksheet 6, so that you can see this as a continuation of earlier ideas. Okay. So let's consider I have a scalar function. In this example, I've got a scalar function of 3 variables. Okay? And I create a level surface. So given a constant C, say a constant, say C, consider this equation. Consider the equation f of x, y, z equals a constant. Okay. Now this, we refer to this as a level set or a level surface, and the idea geometrically is you fed in an arbitrary x, y, and z, so there's 3 degrees of freedom, but then you put a condition on it. That's the equation. So intuitively, if I have solutions, then I'm going to have 2 dimensions worth of solutions. And that object, that set of points that actually solve this equation, they form what we call a surface. Okay? So back when we were starting to learn about calculating the tangent plane to a surface, at a given point, the gradient vector at that point was providing a normal. At the time, I didn't say why that was appropriate, only that it was. And so I want to go back to that basic question. Why is that what I mean by a tangent plane? And it has to do with the chain rule. Okay? So I want to consider the following. Let's what do I want to call it? G from R into R3 be a differentiable function, that whose trace lies in the surface. And my surface here is the set of solutions of this equation. So if I tell you the trace of this curve lies in the surface, what have I said? Well, your curve G, it has 3 components: x of t, y of t, and z of t. Right? And you know how to calculate the derivative of that. You get a velocity vector. Well, what does it mean to say the trace lies in the surface? Well, as I vary time, I'm getting these points. And I'm saying each time your point is actually in the surface. So the defining condition means that for every possible time value, this is a solution to that equation. Okay. So I'm out of space. I'm just about out of space here, but f of x of t, y of t, and z of t, that is a solution. So that's a true sentence, what we call a solution. So as I vary time, I'm getting a different point in 3 space, but it's a point that's on the actual surface. So we say the trace lies in the surface, what it traces out.
And that's just f of g.
And so that's f of g. Right, now you just, so now I'm going to go back to the idea of a composition, which is what you just said to me, Justin, that what have we said here? Well, we have created a composite. We started out with a time parameter. We produced a point, x of t, y of t, and z of t. And then capital F takes you back down to the numbers. But this is a solution to the equation that defines the surface. So when I plug that into F, what do I get? Well, I get C. So I'm getting a fixed number. For example, C could be 0, or it could be 1, whatever that number is. So if I look at this in 2 stages here, I started out with a number, and I ended up with a single number. What kind of function has that property? If I feed in a time value and I always give you out the same number, what kind of function has that? Doesn't matter what time it is, it's always the same output.
Oh, it's just, it's constant.
Constant, right. So I'm going to quit here and say, what's the derivative of a constant?
0.
0. So I know that. I passed Calc 1, right? That's a joke. But now we can look at this in terms of the chain rule, and I'll start with that first thing tomorrow morning. Okay? All right. Thank you, everyone.
Hey, Dr. Fisher. Oh, I emailed you my quiz. I never saw it graded though. I don't know if you had a chance to.
I did grade it, and I thought I returned it to you on Saturday.
Oh, okay. Well, I'm glad you did get it, but I never got the email back. But that's.
Hey, no, I sent it around with a note to everybody. But if somehow, you know, I'm being older in technology, sometimes the two don't agree with each other.
No, it's complicated stuff, man. I have plenty of problems myself. But yeah, I maybe it's too. I ran into this problem when I was trying to email you my exam, and it was like too large or something, and so it
Right.
yeah.
And the Meg file on it was huge.
Okay, I bet that's probably.
When one is creating a PDF, there's a way to have a much more, a file that's very manageable, and I don't know, mine are not that big. And I noticed when I look at the file size for some of you,
It's pretty large.
that's large. I'm saying, what are you doing differently that I'm not doing?
I found out my problem on the first one when I had that issue with you was so I just take a picture with my iPhone and then I air